Alright, grade 11s, welcome to another video. This video is I gotta give a shout out to Kira because I know she really loves my videos and she gave me a lot of positive feedback, which Kira, wow, that's really makes me feel good. That I'm, trying to help you during this time and you support me like that is so nice. And I'm sure the rest of you appreciate it too, especially the way my handwriting looks on this. Anyway, I wanted to give you just some of the next lesson so you can get to do more of the assignments that I gave to you. Anyway, I'm just going to explain this very quickly here. And, we already talked about one of the forces that I'd like to talk about today, which is gravity. So just recall that gravity, the force of gravity anyway, is equal to your weight. So the force of gravity is given by m times g, where g is equal to 9.8 meters per second squared. And of course, that force is down. Okay? So this is equal to what we call your weight. So your weight is a force that we measure in newtons, which is a standard unit of force. All right, so that's the force of gravity on an object. Okay, so that's number one. Number two, okay, surfaces. All right, so when you're sitting on a table or on a chair or there's objects resting on the table, whatever, okay, if you're just standing up, the floor exerts a force on you, okay? The chair you're sitting on exerts a force on you when you sit down on it. A table is exerting a force on the objects that are sitting on the table. And that force is counteracting gravity. In other words, it's acting in the upwards direction. Now, a surface like a table or the floor or even the wall, which is a vertical surface, surfaces can only push. Okay, so surface on surface forces are called, it's a type of contact force. They're called normal forces, and I'll explain why that is in a second. So let's say, here I'll draw a little picture. Let's say we have you. Okay, here, we'll make it here, let's say this is Joseph, okay? So Joseph is standing here like this, and what forces are acting on Joseph when he's just standing still like this? Well, there's really two, and I'll use different colors to represent them. Gravity acts downward on him, but there's a second force, and I'll color it green. The second force is the floor pushing up on him, and we call that a normal force. So this Fn is called a normal force, okay, and it's equal to the force of contact with the floor. Okay, so we call that a normal force. Now, it doesn't mean normal, there's normal forces and then there's weird forces or abnormal forces. That's not what normal means in this case. In math, normal means perpendicular, okay? So let's say you were sitting on a hill. Let's say you're sitting like this. And here's Joseph just sitting down on the hill. Okay, let's say maybe he's sliding down on his butt, down the hill like this. Well, there are still two forces acting on him. One is gravity, okay, and gravity straight down regardless of the inclination of the hill, right? The normal force though, the hill doesn't push him straight up, it pushes him this way, okay? And I haven't drawn it very well, but it pushes him at right angles to the hill, okay? So a surface can only push, and so this normal force, the reason why we call it normal is the word normal means it's perpendicular. Oh, that's terrible. Perpendicular to the surface. Okay? In this case, the surface being the hill, or the floor, whatever the case may be. Okay, or in the case of object on the table, well, it's the table is the surface, right? So anyway, surface on surface contact creates something called a normal force, and that's what the normal force means, okay? Number 3, tension. So let's say you have an object that, I don't know, let's say it's swinging from a rope, okay, like this. So it's a little pendulum or something, or somebody swinging down. Okay, anyway, like an object like this, what kind of forces are acting on it? Well, one, gravity. But this time, this object is not in contact with the floor, but it is in contact with a rope. And ropes create something called tension, and tension pulls on the object. We call it the force of tension. So let me just define that. Ft is the force of tension. Okay, and ropes can only pull. You can't push someone with a rope. So if, like, you and I are holding a rope, you can't push me with it, but you can pull me with it, right? So there's pulling and pushing. Ropes can only pull, right? Whereas a surface can only push. So normal force is a push, but tension is a pull. Okay, like, so in other words, if there's a rope attached, it's always pulling on the direction of itself, never pushing. Okay, so anyway, that is tension. Now that you have this, I want to explain something called Freebody diagram. Okay, so drawing this sort of a separate topic, drawing free body diagrams. And it's a pretty simple concept. It helps you solve problems, which is why I'm explaining it to you. And like, it got me through first year university, believe it or not. It's a really, really powerful way of solving a problem in physics. Now, the problems that we do in grade 11 aren't that hard. Okay, so some people will complain. They'll say, why am I drawing this diagram? It's too easy. I can just do it in my head, or just write down the equation. Trust me, draw the diagram. Okay, I'm going to insist, like, when you're handing stuff in or getting marks for things, I want to see the diagrams drawn for these types of problems. You'll see in a moment what I mean. But it's a really, really powerful thing. There are some problems I could show you in grade 12 that without the diagram, you would not be able to solve it. Like, the diagram is actually part of the process, it's part of the solution. And it helps you to get your mind around some very difficult problems. Now, in grade 11, it's not that hard, but I still want you to do it in practice for grade 12. All right, so look, what is a free body diagram? Pretty simple. One, you draw a box that represents the object. I know you think Kira was telling me how nice my handwriting was and how beautiful my diagrams are. That may be true, but you don't have to be a great artist like me to draw a free body diagram. You just have to be able to draw a box, okay? This box represents the object in question, okay? Number 2, draw vectors on the box indicating the forces acting on the mass. I'll just say on the object. Okay. 3, indicate acceleration with a squiggly line. Okay, a squiggly line looks like that. Isn't that beautiful? Okay. Okay, so that's a squiggly line. And then 4, solve using Fnet equals MA. Okay? And that, in a nutshell, is what got me through first year university physics. It's very, very useful. Like, we're doing really hard pulley questions, which we won't do in grade 11, but we do some of it in grade 12. And without this method, I couldn't have done it. Like, you just can't get your head around it. All right, so with that in mind, okay, let me do some examples. Okay, so here. There's some questions on my assignment that are like this, but let me explain. All right, so let's say, okay, here's a perfect example. A book rests on a table. Okay, what does a free body diagram look like? Well, first of all, it's not going anywhere, so it's not accelerating. Anyway, step one, draw a box. That's the book. Okay, indicate the forces. All right, there's gravity on the book, and because it's on the table, there's a normal force straight up like this, and I'm just going to put on the margin here that the acceleration is 0. Okay. Now, because the acceleration is 0 in this question, what you can do is you can actually solve this. So let's say I told you what the mass was. I won't bother writing it down here, but just let me give you an example. I'm going to treat up as positive. Okay. So the net force on this object is the normal force, and it's going to be minus the force of gravity, right? So this is step 4. I'm solving using F net equals ma. So look, the net force is the sum of the forces acting on the object. Well, that's this positive force, the normal force, minus the negative force, which is, well, I'm adding the negative, so I subtract it. So I've already factored in that gravity is down. Okay? Now, you get this. ma equals Fn minus mg. Now, g is just 9.8, but I've already factored in the negative sign, the fact that I treat it up as positive, and g is negative 9.8. That's why that's minus and not plus. So therefore, if I solve this for the normal force, I get ma plus mg. But a is 0, so that one's 0. So therefore, the normal force is just equal to the weight, right? And we know that, like, in other words, that upward force of the table pushing on the book is equal to the downward force of gravity. That's why the book doesn't go anywhere. That's why it just sits there and stays at rest and doesn't accelerate, because the net force is 0 acting on it. Okay, so this is your free body diagram. And from now on, I'm just going to write FBD, okay, for free body diagram. And that's it. All right, so let me show you something else. Question, here's example number 1. Example number 2. You ride in an elevator. So an elevator with a person accelerates up. Okay. Now, what does that free body diagram look like? Well, the person looks like a box. Actually, here, let me show you what I mean. Let's say this is the person. Okay, and then they're accelerating up like this. This is not a free body diagram because I'm not drawing the person like you're supposed to. You're supposed to just represent the person with a box. So what forces are acting on the person? Well, there's gravity and a normal force. And that's it. There's nothing else touching them, right? Except this time, this is not 0. They're accelerating upwards, okay? And that means, like, see, your weight, this number here, I'm going to circle it in green, that number never changes. That's just your weight. Like, so you don't change weight because your weight doesn't change when you accelerate up or down on an elevator. But this normal force, which I'll circle in blue, that force can change, okay? So when you're in an elevator accelerating upwards, the normal force will be greater than gravity, and that's why you accelerate upwards. You'll feel more contact between your floor and your feet when the elevator accelerates up. That's because that normal force increased, and that allows you to accelerate up. So again, I'll write down the math. The net force, we'll treat up as positive again, is equal to the normal force minus the force of gravity. So ma, we always replace the normal force with the net force, pardon me, with ma, because that's Newton's second law, equals Fn minus mg. Now what will the normal force equal this time? Well, it would be ma plus mg, just like before, except this time a is not 0. And so the normal force is not only balancing gravity, but also providing the additional force for acceleration. Okay, and that's what the math tells you here. Okay. Anyway, so there's a couple of examples of free body diagrams. I want to show you one more. Okay, there's a question in the homework about a spider accelerating downwards on a thread. Okay, and so if I just want to show you that, I'm going to just show it to you here. Okay, so look at question number 2. It says a spider is descending on a strand of web which supports it with a force of this very tiny force, 5.6 times 10 to the negative 4. What's the acceleration of the spider? Okay, well, they give you the mass, it's right there, and they give you the force of tension right there. You can't just put F equals ma. It doesn't work that way. Okay, so look, let me show you. Here's how you do a question like this. So I'm going to go back to my notes. I'm just going to remember that number, 0.1 and 5.6 times 10 to the negative 4. Okay, let's go back here. Whoops, let's go back here. All right, so let's do the spider question. Okay, on a thread, on a little strand of web. All right, so let's do it. Here's the free body diagram of the spider. There's gravity, and there's tension in the web holding them up. It's very much like the elevator question. Now, I don't know which way the spider is accelerating. He could be going up, he could be going down. It depends on which force is bigger. They do give us this one. That one turns out to be 5.6 times 10 to the negative 4. So they tell us that this number is 5.6 times 10 to the negative 4 newtons. Okay. Now, we know that the force of gravity is mg. Okay. Now the spider's mass, and again I forget, so let me go back to it, is 0.1 grams. Well, we have to convert that to kilograms. So the spider's mass is, it's 0.1 grams, which is 0.0001 kilograms. But then I have to multiply that, get rid of the unit. That's its mass. I got to multiply that by 9.8 because the force of gravity is m times g. Okay. All right. So when I do that, let's do that quickly. I mean, I'm just going to get a tiny number. Times 9.8 equals, oh, well, it's 9.8 times 10 to the negative 1, 2, 3, 4, 10 to the negative 4. So this is equal to 9.8 times 10 to the negative 4 newtons. Now I can see already which one's bigger. This downward force is bigger. So therefore, the spider will accelerate downwards. Okay. Now I'm going to make down positive. Okay, so watch. Therefore, the net force, it's the sum of the forces, but because they're in opposite directions, this is my positive force. I'm going to make down positive. That's my choice, right? And you can do what you want, but I'm making down positive. So I get Fg minus Ft. The up force is negative, so that's why I put the negative. Okay, and I get Ma equals Mg minus Ft. Well, I can just substitute these numbers in, and I get 0.0001A equals 9.8 times 10 to the negative 4 minus 5.6 times 10 to the negative 4. Okay, so now just solving it for A. We'll just do it quickly. Plug in all the numbers. 9.8 exponent 4 negative minus 5.6 exponent 4 negative equals divided by 0.0001. And I get 4.2 meters per second squared. And I got a positive number, which means it's down. Okay, now if I go back to my sheet, just to check the answers, I can see that the answer is 4.2 meters per second squared downward. They've treated it down as negative here, but anyway, I would write positive 4.2 meters per second squared downward. And that's how you do a question like that. Okay, so it's really important when you're doing these questions to draw the free body diagram and see if you can figure it out from there. And that's how you do it. Okay. All right, that ends the lesson. That's about 20 minutes, so I like to keep them no longer than that. So yeah, that will end today's lesson. And then tomorrow I will show you how you do if there's 2 dimensions or more than one object in the system. Okay. So we'll stop there for now. Please do the homework. And what I mean by that is look at this homework here. Okay. Right now we can't do the lab, so forget that. Okay, I may or may not with you to do the lab. We're going to be working on these 2 handouts. And then I'm going to figure out how I can test you eventually. Okay, so I'll figure that out. It's not going to be easy, but we'll do something. We'll see. I mean, it'll be probably easier for you to get a good mark, which is a good thing. But anyway, do your best with this, and we'll wrap it up for now. And then after that, we're going to look at 2-dimensional problems. So we're not going to do this near Earth gravity. We're going to work on these handouts for a couple of days. You're going to need my help, I think. So I'm going to figure out what the best way is for me to give you help, because you definitely, I think, need to talk to me. So, I mean, I can write things down for you, but it's a bit difficult to learn that way. All right, so guys, please do the textbook homework. So I'm circling it here. Please, well, here, do all this, okay? And then start working on these handouts. There's a lot to do. If you have questions, maybe I'll get you to post your questions, and I will maybe go through some of them like this. All right, have a good night, or have a good day, and we'll talk to you later.